Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Yvonne Choquet-Bruhat stands as a monumental figure in the mathematical understanding of Einstein's theory of general relativity. Her journey began in a world where mathematical rigor in physics was often secondary to intuitive understanding, and where the landscape of theoretical physics was overwhelmingly populated by men. Born in Lille, France, in 1923, her early life was steeped in the academic atmosphere cultivated by her parents. Her father, Georges Bruhat, was a renowned physics professor, and her mother, a philosophy graduate who actively participated in intellectual discussions. This environment nurtured her precocious intellect and instilled in her a deep appreciation for both the abstract beauty of mathematics and its power to describe the physical universe. The Second World War cast a long shadow over her formative years. The Nazi occupation of France disrupted her education, forcing her to take refuge in the countryside. Despite these hardships, she persevered, eventually gaining admission to the École Normale Supérieure in Paris, one of France's most prestigious institutions of higher learning. There, she distinguished herself in mathematics, demonstrating an exceptional aptitude for abstract thinking and problem solving. The École Normale Supérieure provided a stimulating environment, fostering intellectual curiosity and rigorous training in mathematical analysis, algebra, and geometry. Upon completing her studies, Choquet-Bruhat embarked on a research career, initially focusing on problems in differential geometry and partial differential equations. These areas provided a natural bridge to the burgeoning field of mathematical relativity, which sought to place Einstein's revolutionary theory on a firm mathematical footing. The existing understanding of general relativity, while groundbreaking, suffered from a lack of mathematical precision in certain crucial aspects. Many physicists relied on intuition and physical arguments, sometimes overlooking the need for rigorous proofs and well-defined mathematical structures. One of the central challenges in general relativity was the initial value problem, also known as the Cauchy problem. This problem concerns the prediction of the future evolution of a physical system, such as a star or a universe, given its initial state at a particular moment in time. In the context of general relativity, the initial state is described by the geometry of space and the distribution of matter and energy at an initial time. The question then becomes, does Einstein's field equations uniquely determine the geometry of space-time and the distribution of matter and energy at all future times? The difficulty lies in the highly nonlinear nature of Einstein's field equations, which relate the curvature of space-time to the distribution of matter and energy. These equations are a set of 10 coupled partial differential equations, and their complexity makes it exceedingly difficult to find exact solutions. Furthermore, the very nature of spacetime, as a dynamic entity influenced by gravity, adds another layer of complexity. Prior to Choquet-Bruhat's work, the well-posedness of the initial value problem for Einstein's equations remained an open question. While physicists had developed various approximation methods and numerical techniques to study the evolution of gravitational systems, a rigorous mathematical foundation was lacking. This absence of a solid foundation raised concerns about the reliability and accuracy of these approximations and simulations. It was unclear whether the solutions obtained through these methods were genuine solutions to Einstein's equations or merely artifacts of the approximation schemes. Choquet-Bruhat recognized the importance of addressing this fundamental problem. She saw that a rigorous mathematical framework was essential for making reliable predictions and gaining a deeper understanding of the dynamics of spacetime. She began to tackle the problem by drawing on her expertise in partial differential equations and differential geometry, seeking to adapt existing mathematical techniques to the specific challenges posed by Einstein's theory. Her initial investigations involved analyzing the structure of Einstein's equations and identifying suitable mathematical tools for studying their solutions. She explored various approaches, including the use of function analysis, Sabol of spaces, and other advanced techniques from the theory of partial differential equations. The goal was to establish the existence and uniqueness of solutions to Einstein's equations, given appropriate initial data. This pursuit was fraught with difficulties. The nonlinearity of the equations, the complexity of the spacetime geometry, and the inherent ambiguity in the choice of coordinates all presented formidable obstacles. Many researchers had attempted to tackle this problem, but none had succeeded in providing a complete and rigorous solution. Despite these challenges, Choquet-Bruhat remained undeterred. She approached the problem with a combination of mathematical rigor, physical intuition, and unwavering determination. She spent countless hours poring over equations, developing new mathematical techniques, and refining her arguments. Her dedication and perseverance would eventually lead to a breakthrough that would revolutionize the field of mathematical relativity. In the early 1950s, Choquet-Bruhat began to formulate her ideas on how to approach the Cauchy problem for Einstein's equations. She realized that a crucial step was to rewrite the equations in a form that was more amenable to mathematical analysis. This involved decomposing spacetime into space and time, a procedure known as the 3+1 decomposition. This decomposition allowed her to express Einstein's equations as a set of evolution equations that govern the time evolution of the spatial geometry and the matter fields. The 3+1 decomposition, while not entirely novel, took on a new significance in Choquet-Bruhat's hands. She meticulously analyzed the resulting equations, identifying the principal parts, and determining the appropriate conditions for well-posedness. She recognized that the choice of coordinates, also known as the gauge, played a crucial role in the mathematical properties of the equations. By carefully choosing a suitable gauge, she was able to simplify the equations and make them more tractable. Through this meticulous analysis, Choquet-Bruhat arrived at a groundbreaking result. She proved that, under certain conditions on the initial data and the choice of gauge, Einstein's field equations admit a unique solution that exists for a short period of time. This result, published in 1952, was a major triumph. It provided the first rigorous mathematical proof of the well-posedness of the initial value problem for general relativity. Her solution not only addressed a long-standing problem in mathematical physics, but also laid the foundation for future developments in numerical relativity and gravitational wave physics. The problem of a rigorous mathematical formulation of Einstein's field equations had found a powerful solution. This early work established her as a leading figure in the field and paved the way for her subsequent contributions to general relativity and mathematical physics. Her ability to combine abstract mathematical tools with physical insights allowed her to make significant advances in our understanding of the universe. The problem of a rigorous mathematical mathematical formulation of Einstein's field equations had found a powerful solution. This early work established her as a leading figure in the field and paved the way for her subsequent contributions to general relativity and mathematical physics. Her ability to combine abstract mathematical tools with physical insights allowed her to make significant advances in our understanding of the universe. At the heart of Choquet-Bruhat's initial breakthrough lay a profound engagement with the Cauchy problem, a cornerstone of the theory of partial differential equations. The Cauchy problem, in essence, asks whether one can predict the future state of a system given its present condition. Think of it as trying to determine the trajectory of a ball thrown in the air, knowing its initial position and velocity. For Einstein's field equations, which govern the behavior of gravity in spacetime, the Cauchy problem takes on immense significance. A well-posed initial value formulation would provide a rigorous mathematical framework for understanding the evolution of the universe, the dynamics of black holes, and the propagation of gravitational waves. However, general relativity presented formidable challenges. The equations are highly nonlinear, meaning that the effects of gravity can become self-reinforcing and lead to complex and predictable behavior. Moreover, the equations are diffeomorphism invariant, reflecting the fact that the choice of coordinates used to describe spacetime is arbitrary. This invariance introduces a significant degree of gauge freedom, which can obscure the physical content of the solutions and complicate the mathematical analysis. The absence of a clear understanding of how to handle these difficulties had stalled progress in the field for decades. Physicists and mathematicians alike struggled to find a formulation of the equations suitable for rigorous analysis and numerical computation. They needed a way to disentangle the physical degrees of freedom from gauge artifacts and to establish the existence and uniqueness of solutions given appropriate initial data. Choquet-Bruhat's approach to this problem was both innovative and technically demanding. She recognized that a careful choice of coordinates, or gauge, could simplify the equations and make them more amenable to analysis. She adopted what became known as the 3+1 formalism, a technique for splitting spacetime into space and time. Imagine slicing a loaf of bread. Each slice represents a space at a particular instant of time, and the way these slices are stacked together describes the evolution of spacetime. This decomposition allowed her to rewrite Einstein's field equations as a set of evolution equations, which govern how the spatial geometry changes with time and constrain equations, which must be satisfied at each instant of time. The 3+1 formalism, while not entirely new, became a powerful tool in her hands. She skillfully used it to identify a specific class of gauges, known as harmonic gauges, in which the Einstein equations take on a particularly simple form. In these gauges, the equations resemble wave equations, which are well understood and have been extensively studied. This simplification was a crucial step in her proof of the existence and uniqueness of solutions. For a 1952 paper, Théorème d'existence pour certains systems, the equations, aux dérivées partielles non linéaires, presented a rigorous proof that Einstein's field equations, when expressed in harmonic coordinates and subject to certain conditions on the initial data, possess a unique solution that exists for a short period of time. The proof involved a delicate interplay of techniques from partial differential equations, differential geometry, and functional analysis. She had to carefully control the nonlinear terms in the equations and to establish appropriate estimates on the solutions to ensure that they did not blow up in finite time. The significance of this result cannot be overstated. It provided the first mathematically sound foundation for the study of general relativity as an initial value problem. It demonstrated that Einstein's equations, despite their complexity, are deterministic, meaning that the future evolution of spacetime is uniquely determined by its initial state. This result paved the way for future developments in numerical relativity, a field that uses computers to solve Einstein's equations and simulate astrophysical phenomena such as black hole collisions and gravitational wave emission. Before Choquet-Bruhat's work, numerical relativity was largely a matter of trial and error. Researchers struggled to find stable and accurate numerical schemes, and the results were often unreliable. Her proof of the existence and uniqueness of solutions provided a theoretical justification for these simulations and gave researchers confidence that their results were meaningful. It also provided a framework for developing more sophisticated numerical methods and for understanding the limitations of these methods. The impact of her work extends far beyond the realm of pure mathematics. It has had a profound influence on our understanding of the universe and on our ability to explore its most extreme environments. Today, numerical relativity simulations, based on the mathematical foundation laid by Choquet-Bruhat, are used to model black holes, neutron stars, and other astrophysical objects with unprecedented accuracy. These simulations are essential for interpreting observations from gravitational wave detectors such as LIGO and Virgo, which have opened a new window on the cosmos. Consider, for instance, the problem of modeling the collision of two black holes. This is an extremely complex process that involves strong gravitational fields, high velocities, and nonlinear interactions. Numerical relativity simulations are the only way to accurately predict the outcome of such a collision and to calculate the gravitational waves that are emitted. These calculations are crucial for verifying Einstein's theory of general relativity and for testing alternative theories of gravity. They also provide valuable insights into the physics of black holes and the nature of spacetime. The simulations rely heavily on the mathematical framework developed by Choquet-Bruhat. Her 3+1 formalism is used to decompose spacetime into space and time, and her proof of the existence and uniqueness of solutions ensures that the simulations are stable and accurate. The numerical methods used in these simulations are also based on her work on partial differential equations. Her insights into the behavior of nonlinear wave equations have been invaluable in developing algorithms that can handle the complexities of Einstein's field equations. In essence, her work provided the rigorous mathematical scaffolding upon which the entire edifice of modern numerical relativity is built. It transformed general relativity from a collection of abstract equations into a vibrant field of research with profound implications for our understanding of the universe. The ability to model and simulate gravitational phenomena has revolutionized astrophysics and cosmology, allowing scientists to probe the most extreme environments in the cosmos and to test the fundamental laws of physics with unprecedented precision. The mathematical exploration of partial differential equations formed another cornerstone of Yvonne Choquet-Bruhat's prodigious career, extending far beyond the initial groundbreaking work on the Cauchy problem in general relativity. Her expertise in this area proved invaluable in tackling a range of complex problems in mathematical physics, particularly those arising from the intricacies of Einstein's theory. Einstein's field equations, while elegant in their concise formulation, present formidable challenges to mathematicians and physicists seeking to extract meaningful solutions. These equations are nonlinear partial differential equations, a class of equations notoriously difficult to solve. The nonlinearity implies that the superposition principle, a powerful tool for solving linear equations, is no longer applicable. This means that the sum of two solutions is generally not a solution itself, making it significantly harder to construct general solutions from simpler ones. Furthermore, the equations are coupled, meaning that several unknown functions appear in each equation, further complicating the analysis. The problems of the time demanded advanced mathematical techniques to handle the sheer complexity of Einstein's field equations and related problems in physics. Physicists needed tools to analyze the existence, uniqueness, and properties of solutions to various relativistic problems, providing a solid foundation for theoretical predictions and numerical simulations. Choquet-Bruhat rose to this challenge, developing and applying sophisticated partial differential equation techniques to dissect these intricate problems. Her approach was characterized by a deep understanding of the underlying geometry and physics, combined with a mastery of analytical techniques. She recognized that the key to unlocking the secrets of Einstein's equations lay in a careful analysis of their mathematical structure, particularly their hyperbolic nature. Hyperbolic partial differential equations describe phenomena that propagate with a finite speed, such as waves. This property is crucial in general relativity, where the speed of light plays a fundamental role. Choquet-Bruhat's work on hyperbolic systems provided a powerful framework for studying the evolution of gravitational fields. She developed methods for proving the existence and uniqueness of solutions to these equations, even in situations where the initial data are not perfectly smooth. This was particularly important for dealing with singularities, points where the gravitational field becomes infinitely strong, such as those found in black holes. Her contributions extended to the study of various types of matter fields coupled to gravity, including scalar fields, electromagnetic fields, and fluid dynamics. She investigated the behavior of these fields in curved spacetime, revealing how they interact with gravity and influence the evolution of the universe. This work had significant implications for cosmology, the study of the origin and evolution of the universe, and astrophysics, the study of celestial objects and phenomena. One notable area of her research involved the study of the Einstein-Maxwell equations, which describe the interaction of gravity and electromagnetism. These equations are particularly relevant to the study of charged black holes and other astrophysical objects with strong electromagnetic fields. Choquet-Bruhat's analysis of these equations provided insights into the behavior of electromagnetic radiation in curved spacetime and its effect on the gravitational field. Another significant contribution was her work on the equations of relativistic fluid dynamics. These equations describe the motion of fluids at speeds approaching the speed of light, a situation encountered in many astrophysical environments, such as accretion disks around black holes and neutron stars. Choquet-Bruhat developed methods for solving these equations, providing a theoretical framework for understanding the behavior of matter under extreme conditions. Her insights into partial differential equations also proved crucial in the study of gravitational waves, ripples in spacetime that propagate at the speed of light. The detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, known as LIGO, confirmed a major prediction of Einstein's theory and opened a new window into the universe. Choquet-Bruhat's work on hyperbolic equations laid the foundation for the mathematical analysis of gravitational waves, providing tools for understanding their propagation, generation, and detection. The modern relevance of Choquet-Bruhat's partial differential equation expertise remains profound across diverse fields of mathematical physics. Her methods and techniques continue to be employed in the analysis of nonlinear wave equations, fluid dynamics, and other areas where partial differential equations play a central role. The lasting influence of her approach is evident in modern relativistic research, where her work serves as a cornerstone for theoretical investigations and numerical simulations. Her rigorous mathematical framework provided the necessary tools for physicists to explore the complexities of general relativity and its implications for our understanding of the universe. The ability to analyze the existence, uniqueness, and stability of solutions to Einstein's equations has been instrumental in making predictions about the behavior of black holes, neutron stars, and other extreme astrophysical objects. Furthermore, her work has had a significant impact on the development of numerical relativity, a field that uses computer simulations to solve Einstein's equations. Numerical relativity is essential for studying phenomena that cannot be analyzed analytically, such as the collision of black holes. Choquet-Bruhat's insights into hyperbolic equations have been invaluable in designing stable and accurate numerical schemes for solving Einstein's equations. The development of these numerical methods has revolutionized astrophysics and cosmology, enabling scientists to probe the most extreme environments in the cosmos and test the fundamental laws of physics with unprecedented precision. The ability to model and simulate gravitational phenomena has allowed researchers to study the formation of galaxies, the evolution of the universe, and the behavior of matter under extreme conditions. Her contributions extend to the mathematical theory of black holes, those enigmatic objects whose gravitational pull is so strong that nothing, not even light, can escape. Black holes are predicted by Einstein's theory and have been observed in various astrophysical environments. Choquet-Bruhat's work on partial differential equations has provided insights into the structure and stability of black holes, helping to understand their properties and behavior. She investigated the existence and uniqueness of black hole solutions to Einstein's equations, providing a rigorous mathematical foundation for the study of these objects. Her analysis of the stability of black holes has been crucial in understanding their response to perturbations, such as those caused by the inflow of matter or the collision with other black holes. Her work on partial differential equations has also found applications in the study of cosmology, the science of the universe's origin and development. Cosmological models are based on Einstein's equations and describe the evolution of the universe from its earliest moments to the present day. Choquet-Bruhat's expertise in partial differential equations has been instrumental in analyzing the stability and properties of these models, providing insights into the large-scale structure of the universe and its ultimate fate. She investigated the behavior of cosmological solutions to Einstein's equations, including those that describe the expansion of the universe and the formation of galaxies. Her analysis of the stability of these solutions has been crucial in understanding the conditions under which the universe can evolve into its present state. In essence, Yvonne Choquet-Bruhat's contributions to the mathematical theory of partial differential equations and their applications to general relativity represent a monumental achievement. Her work has not only advanced our understanding of the fundamental laws of physics, but has also provided the mathematical tools necessary to explore the most extreme environments in the cosmos. The continued relevance of her expertise in partial differential equations ensures her enduring legacy as one of the most influential mathematicians and physicists of the 20th and 21st centuries. Yvonne Choquet-Bruhat's scientific journey, while marked by individual brilliance, also exemplifies the power of collaboration in scientific advancement. Her interactions with other leading researchers, particularly physicists, enriched her mathematical insights and propelled the field of general relativity forward. These partnerships were instrumental in translating abstract theoretical constructs into tangible models of the universe. One particularly fruitful collaboration involved her work with physicists researching gravitational waves. At the time, the theoretical framework for gravitational waves, ripples in spacetime predicted by Einstein's theory, was well established. However, challenges remained in detecting and interpreting these faint signals. Choquet-Bruhat's expertise in solving Einstein's field equations, specifically under conditions relevant to gravitational wave propagation, proved invaluable. She provided rigorous mathematical justifications for approximation methods used in detecting these waves, ensuring the validity of techniques employed by experimental physicists. This collaboration bridged the gap between theoretical predictions and experimental observations, contributing significantly to the eventual confirmation of gravitational waves. Her collaborative spirit extended to researchers exploring the initial singularity, the hypothetical point of infinite density and temperature at the beginning of the universe. The study of singularities requires sophisticated mathematical tools to handle the extreme conditions involved. Choquet-Bruhat's deep understanding of hyperbolic partial differential equations and their application to general relativity enabled her to analyze the behavior of spacetime near singularities. She worked alongside cosmologists to develop mathematical models that could probe the nature of these singularities, shedding light on the earliest moments of the universe. This interdisciplinary approach, combining mathematical rigor with physical intuition, offered a deeper understanding of the universe's origins. Choquet-Bruhat also engaged in collaborative efforts to investigate the stability of black holes. Black holes, regions of spacetime where gravity is so strong that nothing, including light, can escape, present formidable mathematical challenges. Determining whether these objects are stable, meaning they return to their original state after being perturbed, is crucial for understanding their role in the universe. Her work with mathematical physicists involved applying advanced techniques for partial differential equations to analyze the behavior of black holes under various perturbations. These collaborations led to significant progress in understanding the stability properties of black holes, confirming theoretical predictions, and providing insights into their long-term evolution. The collaborative nature of her research extended to the study of cosmological models. She worked with astronomers and astrophysicists to develop and analyze mathematical models of the universe, including those that incorporate dark matter and dark energy. These models are essential for understanding the large-scale structure of the universe and its evolution over time. Choquet-Bruhat's expertise in solving Einstein's equations for complex cosmological scenarios allowed her to provide rigorous mathematical foundations for these models. Her contributions helped refine our understanding of the universe's composition, expansion rate, and ultimate fate. Her collaborations were not confined to established figures. She actively mentored and collaborated with younger researchers, fostering a new generation of mathematicians and physicists working on general relativity. This commitment to collaboration and mentorship ensured the continued growth and vitality of the field. Her open and supportive approach created an environment where ideas could be freely exchanged and developed, leading to innovative breakthroughs. A specific example of this collaborative mentorship can be seen in her work with students on numerical relativity. Numerical relativity involves using computer simulations to solve Einstein's equations in situations where analytical solutions are unavailable. This approach is crucial for studying phenomena such as black hole mergers and the dynamics of neutron stars. Choquet-Bruhat guided students in developing and implementing numerical algorithms to solve these complex problems, providing them with the mathematical tools and physical insights necessary to make significant contributions to the field. This hands-on approach fostered a deeper understanding of general relativity and prepared students to tackle the challenges of modern astrophysics. Another notable collaboration involved her work on the Cauchy problem in general relativity. The Cauchy problem, also known as the initial value problem, concerns the existence and uniqueness of solutions to Einstein's equations given initial data on a space-like hypersurface. This problem is fundamental to understanding the predictability of general relativity and the evolution of spacetime. Choquet-Bruhat's work with mathematicians and physicists led to significant advances in the understanding of the Cauchy problem, providing rigorous mathematical proofs of the existence and uniqueness of solutions under various conditions. These results have profound implications for our understanding of the nature of spacetime and the limits of predictability in the universe. The impact of her collaborative work extends beyond specific research projects. Her ability to bridge the gap between mathematics and physics has fostered a greater appreciation for the importance of interdisciplinary collaboration in scientific research. She demonstrated how abstract mathematical concepts can be applied to solve real-world problems in physics, and how physical intuition can guide the development of new mathematical tools. This interdisciplinary approach has become increasingly important in modern science, where complex problems often require expertise from multiple fields. Her collaborative spirit also played a crucial role in promoting the participation of women in science. As a pioneering female mathematician and physicist, she served as a role model for aspiring scientists around the world. Her success demonstrated that women can excel in these fields and make significant contributions to our understanding of the universe. She actively supported and mentored other women in science, creating opportunities for them to pursue their passions and achieve their full potential. The problems of her time demanded a synthesis of mathematical rigor and physical insight. General relativity, while elegant in its formulation, presented formidable challenges in its application to real-world phenomena. Choquet-Bruhat's unique solution lay in her ability to seamlessly integrate mathematical techniques with physical intuition, fostering collaborations that bridge the gap between theory and observation. This approach not only advanced our understanding of general relativity, but also served as a model for interdisciplinary collaboration in science. The modern relevance of her collaborative efforts lies in the enduring importance of interdisciplinary research. Many of the most pressing scientific challenges of our time, such as understanding climate change, developing new energy sources, and curing diseases, require expertise from multiple fields. Choquet-Bruhat's legacy serves as a reminder of the power of collaboration and the importance of fostering a culture of open communication and shared knowledge. Her work continues to inspire scientists to work together to solve the complex problems facing our world. Yvonne Choquet-Bruhat's profound impact resonates across mathematics and physics, a testament to her intellectual prowess and unwavering dedication. Her work fundamentally reshaped our understanding of Einstein's theory of general relativity, providing the mathematical framework necessary for its rigorous analysis and application. The ripples of her contributions continue to be felt in contemporary research, shaping the direction of gravitational physics and cosmology. The enduring significance of Choquet-Bruhat's work stems from its mathematical depth and its physical relevance. She provided the necessary tools to explore some of the universe's most enigmatic phenomena, from black holes to gravitational waves. Her insights into the well-posedness of the Einstein equations laid the foundation for numerical simulations of these phenomena, enabling scientists to test theoretical predictions against observational data. This paved the way for a deeper understanding of the cosmos, allowing us to probe the universe's most extreme environments. Her legacy extends far beyond her specific mathematical results. Choquet-Bruhat served as a role model for generations of scientists, particularly women, demonstrating that intellectual brilliance knows no gender. Her journey through the male-dominated world of mathematics and physics was marked by perseverance, resilience, and an unwavering commitment to excellence. She shattered barriers and paved the way for future generations of female scientists to pursue their passions and make their own contributions to our understanding of the universe. The broader implications of Choquet-Bruhat's pioneering work lie in its demonstration of the power of mathematical rigor in physics. She showed that abstract mathematical concepts can have profound implications for our understanding of the physical world. Her work serves as a reminder that mathematics is not merely a tool for solving problems, but also a source of inspiration and insight. It provides a language for describing the universe's deepest secrets. The continued relevance of Choquet-Bruhat's contributions is evident in the ongoing research on general relativity and cosmology. Her work continues to be cited and used by scientists around the world. Her mathematical techniques are essential for analyzing data from gravitational wave detectors, such as LIGO and Virgo. These detectors have opened a new window on the universe, allowing us to observe the collisions of black holes and neutron stars. Choquet-Bruhat's work provides the theoretical foundation for interpreting these observations and extracting valuable information about the nature of gravity and the evolution of the cosmos. Her influence extends to the development of new mathematical tools and techniques. The methods she developed for analyzing the Einstein equations have been generalized and applied to other areas of physics and mathematics. Her work has inspired new research in areas such as partial differential equations, differential geometry, and numerical analysis. Her legacy is intertwined with the advancement of mathematical knowledge itself. Choquet-Bruhat's place in the history of science is secure. She is recognized as one of the most important figures in the development of general relativity. Her work has had a lasting impact on our understanding of the universe. Her contributions have been recognized with numerous awards and honors, including the French Academy of Sciences Hemi Poincaré Prize and the American Mathematical Society's Steele Prize for Mathematical Exposition. These accolades reflect the profound significance of her work and its lasting impact on the scientific community. Her influence on future generations of scientists is immeasurable. She inspired countless students to pursue careers in mathematics and physics. Her lectures were renowned for their clarity, rigor, and enthusiasm. She mentored many young scientists who have gone on to make their own significant contributions to the field. She leaves behind a legacy of intellectual curiosity, dedication, and excellence. The long-term significance of Choquet-Bruhat's contributions lies in their fundamental nature. She provided the mathematical foundations for our understanding of gravity and the universe. Her work will continue to be relevant as long as scientists continue to explore the cosmos. Her insights into the nature of spacetime and the behavior of black holes will remain essential for future generations of physicists and mathematicians. Her lasting impact on our understanding of the universe is undeniable. She helped to transform general relativity from a theoretical curiosity into a powerful tool for understanding the cosmos. Her work has enabled us to probe the universe's most extreme environments, test the predictions of Einstein's theory, and gain new insights into the nature of gravity. Her contributions have fundamentally altered our view of the universe and our place within it. Choquet-Bruhat's journey serves as an inspiration to all who strive to push the boundaries of human knowledge. Her story is a testament to the power of perseverance, dedication, and intellectual curiosity. She demonstrated that with hard work and determination, it is possible to overcome obstacles and make significant contributions to our understanding of the world. Her life and work serve as a reminder that the pursuit of knowledge is a noble endeavor and that the rewards of scientific discovery are immeasurable. Her accomplishments stand as a beacon, illuminating the path for aspiring scientists and mathematicians. Her work underscores the importance of rigorous mathematical analysis in understanding the physical world. It highlights the power of collaboration and the importance of fostering a culture of open communication and shared knowledge. Her legacy serves as a reminder that the pursuit of scientific knowledge is a collective endeavor and that the greatest discoveries are often made through the combined efforts of many individuals. The brilliance of Yvonne Choquet-Bruhat's contributions to mathematics and physics continues to shine brightly, shaping our understanding of the universe and inspiring generations of scientists to come. Her legacy is not merely a collection of theorems and equations, but a testament to the power of the human intellect to unravel the mysteries of the cosmos. This legacy endures, a vibrant and vital force in the ongoing quest to comprehend the fundamental laws that govern our universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.